Hello everyone, welcome back to the channel. This video is about the transformer equivalent circuits. I'm going to discuss the referred circuits of the transformer. Now referred circuits means we can refer the transformer on the primary side, means the secondary side resistance, reactance or the load, all the quantities will be expressed on the primary side, and similarly we can do it on the secondary side. The basic purpose is to eliminate the ideal transformer from the equivalent circuit of the practical transformer. The exact equivalent of practical transformer was discussed in the previous video. If you haven't checked that video, you can check from the link which is available in the description box. Also, I will obtain the approximate equivalent circuit from the exact equivalent circuit of the transformer and refer that also on the primary side as well as on the secondary side. But before we do the referring from one side to another side, we need to just revise the transformation ratio, which is given as V1 upon V2. And if we want to write this transformation ratio in terms of current, then it will be equal to I2 upon I1. So when we need to refer the quantities from one side to another side, then basically we mean that we have to scale the voltage, current as well as impedance from one side to another side, from the level of voltage from one side to another level of voltage on the other side of transformer. We can refer on primary side or we can refer it on secondary side. So we know that these two expressions will help us in changing the level of voltage and current. Using these two expressions, we can also change the impedance. Now let's say Z1 is the primary side impedance. So it will be equal to V1 upon I1. Now I want to shift this or refer this to secondary side. Then it will be denoted by Z1 dash, which is actually primary side impedance referred to secondary side. Now when this impedance is referred on secondary side, then it will be equal to V2 upon I2. Now we can express this V2 in terms of V1 from here. So V2 will be equal to V1 by A. From here we can express I2 in terms of I1. It will be equal to A into I1. So Z1 dash becomes 1 upon A square into V1 by I1. V1 by I1 is Z1. So we can write Z1 dash is equal to Z1 upon A square. Since this is a transformation for impedance, it is equally equivalent to the applicable to the resistance. We can write R1 dash is equal to R1 by A square as well as reactance. So X1 dash can be written as X1 by A square. So R1 is the primary side resistance referred to secondary side and X1 dash is the primary side reactance referred to secondary side. Similarly, we can refer the secondary side impedance on the primary side. Let's say secondary side impedance is Z2. It will be equal to secondary side voltage upon secondary side current. Now we want to refer it on the primary side. It will be denoted by Z2 dash. So Z2 dash is secondary side impedance referred to primary side. So when Z2 dash is referred on primary side, it will be actually ratio of primary side voltage to primary side current. Now V1 can be written as A times V2 from here. So A times V2. And if we want to write I1 will be equal to I2 by A. So this Z2 dash becomes A square into V2 upon I2, where V2 upon I2 is Z2. So Z2 dash is equals to A square into Z2. So similar to primary side, this transformation is equally applicable to the resistance of the secondary side. So secondary side resistance referred to primary side denoted by R2 dash is A square into R2. X2 dash secondary side reactance referred on primary side is A square into X2. Similarly, we can do it for the load impedance. So ZL dash will be equal to A square into ZL. So using these, we can refer the equivalent circuit from one side to another side. Now, firstly, we have to draw the exact equivalent circuit. Now, the exact equivalent circuit is that we have a resistance on the primary side, reactance on the primary side, supply voltage V1, resistance R1, reactance X1, then followed by shunt branch RC and XM. Then we have the representation of transformer, which is actually the representation of an ideal transformer. So actually we need to eliminate this. Then on secondary side reactance, resistance, and then we have a load ZL over here, across which voltage is V2. Here the current is I2. Here it's I1 dash, I0, IC, IM, and here the current is I1. Now when we have to refer it on the primary side, so what we can do, we can eliminate this ideal transformer. Primary side quantities will remain as it is. There is no change in R1, X1, RC, XM, but the secondary side reactance as well as the resistance, they will be referred on the primary side. So it will be written as JX2 dash, R2 dash, impedance ZL dash, and here we have applied voltage V1, I0, IC, IM, this is I1 dash. Across this the voltage is now V2 dash. Now what's the value of V2 dash? V2 dash is A times V2. The value of R2 dash is A square into R2. X2 dash is A square into X2, where A is equals to V1 by V2, or we can write this one is equal to N1 by N2. So basically we need to know that the turns ratio. ZL dash is equals to A square into ZL. Now this equivalent circuit can be actually approximated. Now how can we do the approximation? Here the current is I1. We know that this I naught current is just 2 to 5% of I1. So if we shift this shunt branch before the primary side resistance and reactance, that will actually lead to an approximate equivalent circuit. So basically what we are saying that this voltage drop across R1 and JX1, that is almost same if current I1 is flowing or whether current I1 dash is flowing through the resistance and reactance of the primary side. So when we do this approximation, so that will give us a circuit which is easy to analyze in comparison to the one which I had already drawn. So we can shift the shunt branch before the series parameters RC, JXM. Then we have JX1, R1, JX2 dash, R2, and here we have ZL dash. Now, since two resistances are connected in series and two reactances are connected in series, it can be shown like this, that we have a single resistance and single reactance. Where this one is R equivalent 1 and this is JX equivalent 1. R equivalent 1 is the equivalent resistance of the primary side, which is equal to R1 plus R2 dash, R1 plus A square into R2. X equivalent is X1 plus X2 dash, which is equal to X1 plus A square into X2. The equivalent reactance of the primary side and the equivalent resistance of the primary side. They can be calculated from these two expressions. Similarly, we can refer the equivalent circuit on the secondary side. Equivalent circuit referred to secondary. So when we have to refer it on secondary side, we had already seen that how we can refer. So whether it's a series branch or the shunt branch, every term will be, every element will be referred on the secondary side. So we have resistance, reactance, then we have shunt branch, and then we have the load impedance across which voltage is V2. This will be RC dash, J, XM dash, R1 dash, J, X1 dash, R2 and J, X2. Current over here is I2, this will be I naught dash, this will be I1 dash. Applied voltage will become, instead of V1, it will be replaced by V1 dash. Here we have applied voltage, which is V1 dash. Now we can write the value of V1 dash. V1 dash will be equal to V1 by A. Again, A is N1 by N2. I had already discussed that how we do the transformation. So we can easily write that V1 dash is equal to V1 by A. I1 dash is equals to A into I1. I naught will be equal to A in I naught dash will be equal to A into I naught. And the core loss component of current IC dash, and here we will have current IM dash. IC dash will be equal to A into IC, IM dash will be equal to A into IM. Same transformation for all currents. R1 dash will be equal to R1 by A square. X1 dash will be equal to X1 by A square. RC dash RC by A square. XM dash XM by A square. So all transformations are same. Now this circuit can also be approximated by shifting the shunt branch before the primary side resistance and the reactance, that is before R1 dash and X1 dash. So when we do the shifting of shunt branch, that is known as approximate equivalent circuit. So the approximate equivalent circuit looks like this. So here we have applied voltage V1 dash, R1 dash, JX1 dash, R2, JX2, JXM dash, RC dash, I0 dash over here, I1 dash, the current is I2, IC dash and I dash. And here we have the load impedance ZL across which the voltage is V2. So this is a approximate equivalent refer to secondary side. So it can be drawn like a more simple way by a single resistance RE2, equivalent resistance XE2, and here we have shunt branch RC dash XM dash ZL and the supply voltage V1 dash, where this RE2 is equals to R1 dash plus R2. R1 dash is R1 by A square plus R2. XE2 is equals to X1 dash plus X2, which is equal to X1 by A square plus X2. So from approximate equivalent circuit, if we eliminate the shunt branch, since current I0 is very small, then the equivalent circuit becomes very simple, which is known as simplified circuit, which can be shown like this. That we have a single resistance and single reactance. So if they are referred on primary side, then this is the simplified equivalent referred to primary side, or it can be drawn on the secondary side as well, where it will be E1 dash RE2 XE2 ZL. So this is again simplified equivalent refer to secondary side. This is simplified equivalent circuit refer to primary, or second simplified equivalent circuit refer to secondary side. Now these simplified equivalent circuits, they are helpful in calculating the voltage regulation that I will discuss in the coming videos. In this, I have expressed the equivalent circuits in terms of primary or secondary. The equivalent circuits can be referred to the high voltage side or the low voltage side by scaling down the voltage and current as well as the impedance in terms of low voltage or high voltage, depending upon that how we want to refer. In the next video, I will discuss the efficiency losses occurring in the transformer and how to calculate them. Thanks for watching the video.